Okay, so today we're gonna get into combustion turbines. That's your chapter 5. So, you can take a look at these combustion turbines. So this is one of them. Um, the whole, system is designed to be able to start very quickly. Okay, and that's very important, especially during the peak operation periods. So again, the system is designed to start quickly. Okay, gotta start quickly to meet the demands, all right, for your electricity. So this system, we use natural gas. So you can see right here, natural gas line is going right in, and that's the fuel for the entire system. Sometimes, and here you can read right here, low sulfur fuel oil. Okay, you can use this as well instead of natural gas. Again, your fuel type depends on your business, depends on your design, and depends on what you're doing. Okay, but most of the time we use natural gas. Of course, the turbine, they operate like nearest example is your engine, your jet engine. So what this system does, it's going to draw in the air, okay, in front of the unit. So you can see right here in this diagram, see? So this is your air intake. So this is what we're saying right here. They draw in air at the front of the unit. This is the front, and that is your back. And here you have your combustion chambers, and we compress it in this chamber, mix it. You can see right there, your fuel line is in it, see? So we mix it with the fuel. Then we're going to ignite it. So when you ignite it, your turbine is going to start, yeah? And we call it the hot combustion gases. Right there, it's happening inside of this chamber. And they're going to expand through these turbine blades, okay? So when you take a look at the system, you see these blades or turbines are connected to the generator right there. See how the power is transferred, or we can say energy is converted from the fuel, use the air, burn it, okay, ignite it, expand it. We're expanding this guy, yeah? And we're going to operate the turbine, which is connected to generator, and use that mechanical energy, okay? So generator, what are we doing? We're producing electricity. So this is what we're saying right there, the demand for electricity, yeah? And the entire system efficiency is because we can start it quickly. So even your car engine is the same, okay? The system is the same. So what we're doing is you're heating, okay? You're heating the air. Make sure you understand the compression. That's like increasing the pressure, and it's so important. This is how we convert the regular air to the energy, okay, energetic. So meaning like very active, okay, active gases, you can compress it. So they goes like into a very, very small space, and you fuel it, ignite it, so they will expand. When they expand, you get your energy, okay? It's very, very powerful. Combustion is incredibly powerful. It can carry your entire car. Everything that you load up on your car is going that way. The same thing, the turbine, just a bigger, yeah, more localized system. But pretty similar to your car engine, jet engine, okay? We got the small thing right here in our car. The plane engine, they got a little bit bigger. The only difference is like the systems get sizes bigger and bigger. And here, of course, we're running. You need a lot of energy to run the generator for electricity. So that power, that mechanical power, okay, can be produced in this way. Okay, it's very cheap. Air is completely free anyway. This one is you have to import. No, sorry, natural gas we make it here. So pay attention to the fuel. Here we mention only two, but not limited to natural gas or low sulfur fuel oil. And this textbook just simplifies. Okay, it depends on the system. Sometimes you use different types of fuel like petroleum and things like that. Okay, but of course we in 21st century natural gas is better. So the turbine, combustion turbine, okay, they're very complex system, but we can break it down into three parts. Yeah, the first one is your compressor. In your previous diagram, okay, you remember there's a compression chamber at the middle of the system, and then your combustion system, which is where all your gas and the fuel mix up and ignite, yeah, ignite it, and then your turbine is your blades, okay, which is going to be connected to generator in your previous whatever that you want to use your mechanical energy, okay, for. So again, three parts: compressor, combustion system, and then your turbine. Okay, so the very first one, right, is your compressor. So what it does, it draws the air, right, into the engine, and then we're gonna pressurize it, meaning like compress the air. We don't want to lose air. You want to compact it first, and then you're gonna feed it to the combustion chamber, meaning like we are heating it, okay, by using your fuel of some type. And this is just telling you, okay, how fast, alright, that pressurizing speed is. It's like hundreds of miles per hour is going on, right, in that compression chamber. Yeah. So when you think about it, so inside of the chamber like that, and we got your air right there, okay, completely pressurized, meaning like when you pressurize it, okay, they go crazy right in there and they won't move. That's your kinetic energy. So as they move, as they heat it, okay, with a fuel, some type of fuel, natural gas, okay, or oil, and they're gonna start to expand because the movement, we call it temperature, the movement of these particles. Here our particles are air, yeah, air molecules. So they go aggressively and start pushing, right, inside of that chamber, and that energy can be able to move these gigantic blades. Okay, we can't move. You and I cannot be able to physically move this, but your air molecules and the atoms are in there. You can't even see them, but they can move this. Okay? And all you need to do is to expand it, which is heating it, heating them up. And they have smaller things, they have more powerful energy than we ever have. Okay? We're very bulky. Our system is so bulky. And the energy we can be able to apply or exert cannot be able to compare to these guys. Yeah? They're powerful, very, very powerful. So anyway, that's what's going on inside of it, right? The combustion chamber, and that job is done by the compressor, which is a component in your combustion turbine. Okay, so it's happening right here behind. You can't really see it at the front. You can only see right there as blades. Okay, so the next component is your combustion system. So here in this system, we have injectors. Okay, and injectors, we inject the fuel, natural gas or something else, yeah, into that chamber. And then we're going to mix that fuel with the air, yeah? And then we're going to burn it, okay? Burn that mixture at 2000 degree Fahrenheit. Don't forget there are two units, yeah, temperature units. One is a degree Celsius, and this one is a degree Fahrenheit, yeah. Usually degree Fahrenheit has really big numbers, yeah. Degree Celsius more compact. So inside of that chamber, I've already told you what's going on is your pressure, okay, very, very high pressure, because you are compressing the air mixed with the fuel, yeah, at a very, very high temperature, meaning you're heating them up, yeah, heating them up, so in order to extract energy to move these things. And that is, of course, connected the expansion of your gas got to be used through, okay, got to go through this turbine to move these blades to produce the mechanical energy. Alright, so the third component is your turbine. So they're just blades, okay, and they can rotate. So we call them rotating aerofoil section blades. So it's just right here, okay. They're very big, okay. You also have some small turbines. It depends on the system. So anyway, these systems right here are very big systems, and these blades are very, very heavy, okay. If you look at the picture, you're like, whatever. But it's a giant system. Then we're gonna use that, right, to expand it, the very, very hot, okay, air mixture, and that is gonna expand through this turbine, okay. So use that energy to rotate these blades, yeah. So you've got the idea. I'm telling you again and again the same thing. Okay, so function. So what it does. First thing, of course, is to generate the electricity, yeah. So you're gonna use that mechanical energy, yeah, and we're gonna run the generator. So here we're ready to spin a generator. And generator function is to produce electricity, turning mechanical energy into electrical energy, okay. So electricity is nothing but we are moving another type of smaller particles, which is your electrons, yeah? Alright, then the second function of your blades, okay, right here, rotating blades. So that mechanical energy we use to drive the compressor, okay, to draw more air into the combustion chamber, okay. So you can be able to continuously generate the mechanical energy to run the generator, okay. So even though it is a turbine, right, connected between the generator and the combustion chamber, this mechanical energy is used for both of them, yeah, electricity generation and also drawing, okay, the air into the compressor. We're gonna briefly get into land-based gas turbines, yeah. Land-based meaning like we're not using these turbines in the jet engine or somewhere else that is, okay, off land, yeah. So this is land-based, so we have two. So one is a very heavy frame engines and the other one is aeroderivative engines, okay. Derivative is nothing but we're based, okay, on these engines or the design of these engines are based on your, okay, aero turbines, right? So we call it aeroderivative engines. Alright, so heavy frame. So heavy frame engines. So they are made, okay, by using the low pressure ratios. So here I'm just saying, oh, these engines are characterized by low pressure ratios. You already knew the pressure is very important in compression, okay? You gotta play with the pressure, and every time you play with the pressure, your math, okay, mathematics, so these ratios are very important. So what we do in this engine, in this type of heavy frame engine, is to lower that ratio, okay? Okay, so what is that ratio? I'm gonna draw this for you right here. So it's right here, okay? Telling you the ratio is the ratio of the compressor discharge pressure, okay? So we have a dP So that's called discharge pressure. And then we have our air in, okay, which is your inlet air. So I'm gonna write it here, inlet pressure, okay, IAP. So discharge, I just let that compressed air go, and the other one is taking in, which is your inlet air pressure, okay, coming in, and this is letting go. So this ratio got to be reduced. So reducing the pressure ratio, meaning like making this bigger, yeah. So if you make this bigger, the entire ratio will reduce. So that's just your mathematics review. Okay, take time to go back, and then you can put number here, yeah, increase this one, and you're gonna see the ratio is going to gradually reduce. Yeah, all right. Because these engines, all right, they have very, very high power output. So they will definitely produce, okay, large amounts of emission. So that's one thing not very good. And so it must be designed, alright, to satisfy what we're doing, low emission, yeah. Gender, all of the carbon zero emission, things like that. So you gotta redesign in order to reduce this, okay, emission rate and also the amount. Okay, so what kind of emissions, alright, we got from these engines? So that's nitrogen oxide and nitrogen dioxide. Okay, nitrogen, if you have only N2, yeah, so that's what we have in the air that we breathe. N2 is inert. So inert meaning like it doesn't do anything to your body system, and you can breathe in and out, it doesn't really matter, yeah. But what we want is oxygen, of course, for our system to continue to live and survive, because our blood system needs it. This one is really inert. It doesn't do anything. Also, your atmosphere, right, all over the world. This is my Earth right here, planet. So I'm just going to put an E. So nitrogen is in your atmosphere, right in there. Okay, a lot of them, the highest percentage in the air. And it definitely cushions that atmosphere. So even if we have oxygen and temperature, okay, going up sometimes, our planet is not burning, okay. Why? Because of this inner gas, right? Completely making they serve as cushion. We call it as cushion, so the fire won't start right away, because oxygen, it definitely is no good. So if you have more oxygen in the environment and you have forest fire or something, it's going to definitely support that fire to grow bigger, yeah. So if you have nitrogen, okay, so some of the fire fighting, okay, method or approach, you can spray, all right, nitrogen. So these are new technique, because they will definitely cushion and probably stop the fire, okay. So don't worry so much about your chemical stuff. If you remember my nitrogen, okay, one oxygen is mono, so therefore monoxide. Nitrogen 2 oxygen is di, so nitrogen dioxide, okay. If you get that for your emission types, you're okay. Alright, so here is just showing you a picture of how big your heavy duty gas turbine is, and you can see here is a man right there, see, and that's gigantic system right there, yeah. Okay. Okay, then we're getting into aeroderivative engines. So these engines are, they derive, again, of course, aero, so jet engines, okay? And they can operate at very high compression ratio, okay? The ratio that your DP and IAP, okay? So that ratio, again, here is your key point, very high for aero, okay, derivative engines. The other one is low, yeah? Ratio is low, so this ratio is very high. So take into that key point in excess of 30, yeah? And these engines, they tend to be very compact, okay? So everything that goes with aero, everything that goes with jet, got to be light and compact. You don't want to put everything so heavy right up there, even though we call it okay heavy, but you still have to calculate with the weight of your air mass in the atmosphere. Okay, so whatever you're putting into the atmosphere, okay, got to be lighter than your air mass. So your air, okay, can be able to lift that up. Yeah, air is very actually heavy. Yeah, we think like air is nothing, it's weightless or something, but it has tremendous weight. Okay, so if you do skydiving, you can feel that force. Okay, you can feel the force of the atmosphere all around you. Okay, because there are particles inside of the atmosphere. Yeah, so what are the particles? You can see them with your eyes. They come down in the form of rain. They come down in the form of snow. Okay, so snow are just like white sand, right? Cold and white sand, and you can see every time snow falls, you can see a whole bunch of stuff right on your road, everywhere. So that's if you weigh the snow, it's very heavy, and these are the stuff inside of your atmosphere. Okay, so therefore air mass is very very okay high. Yeah, that's the reason why it can carry your plane, it can carry all of your luggages inside of the plane, it can carry you and all the passengers inside of the plane. Yes, with no issue. Yeah, so make sure that you understand the mass of the air in the atmosphere is very heavy. Of course, that's the reason why it can be able to exert force to hold you up. Yeah. Okay, so since they're very compact, they're very useful, and they need a whole lot of maintenance, and of course, their power output is also smaller. Yeah. So we use if you need a smaller power output, you're gonna go with aeroderivative engines. And we use these engines, okay, to drive compressors, fuel type, your natural gas pipeline, okay, power ships, and they also give you peak power, okay, intermittent power for electric utility applications. These are just like where we apply these. So the advantage, okay, principal advantages of gas turbines. So even though we call it like, like if you need, we can use the gas turbines in many different kinds of applications. But we use them like if you need really, really large amount, okay, of power. Why? Because gas turbines, they're small, okay. Also, they have less weight, okay, than other systems. So for a relatively small size and weight, okay, for these turbines, they can be able to produce large amounts of useful power. So that's their capability, okay, and that is the advantage of them. Yeah, and we use them a lot. Okay, so other stuff. So if you think about the turbine, right, the motion is totally rotation, right? Rotational motion or rotation. So meaning like that kind of motion, right, is not reciprocating motion, it's just rotation. Reciprocating motion, you can see that type of motion in piston, right, engine. It's a different type of engine. And gas turbine, they have long mechanical life, and that you don't have to take care of it, meaning like maintenance cost is very low. Okay, they function very efficiently. So the next good thing about gas turbine is the setup time. Okay, so setup time is really short. Okay, you need, of course, another external motor, or you need another small gas turbine to start. Okay, to start it. But you can set that up in a few minutes. Okay, if you compare it to the steam turbine, not gas turbine, but steam turbine. So these steam turbines, they need, okay, more setup time. Okay, setup time is you set up the system, okay, in order for it to operate, okay, fully. Here in this book, they go by start up time, but it's the same thing. We call it set up time, okay, for operation of any kind of engine or system. Okay, so all right. You can use another advantage is you can use different types of fuel, and we already know we can use natural gas, so that's a very common type, yeah, for land-based gas turbines. In our first slide, we have sulfur, yeah, low sulfur oil. You can also use a light distillate oil for your airplane, okay, gas turbines. We can use a diesel oil, okay, and treated residual oil. You can also use combustible gases, all right, direct combustible gases into the chamber, and we can collect these gases from the furnaces, right, refineries, and also solid fuels. Okay, you can get the gas out of these fuels. So solid fuels are your coal, your wood, right? You can burn it. So if you burn your coal and wood, is going to go through the gasification, which is like turning right solid into gas. So it's very convenient, right? These turbines are, because it can take in different types, right, of fuel. And other type, okay, is you have the gases. It's the same thing, like you burn, right? The sugar cane remains, right? Fibers. These are just, so I would just put it into wood, right, category, instead of taking it out. But it's the same thing. They just want to know you what that is. Yeah, that's just a fibrous matter, meaning like wood-like stuff, right? Remains after you use your sugar cane or softened stalks and can crush it, extract that juice. So sugar cane, you use it for making sugar. Some people like to drink sugar cane juice. It's very delicious. Okay. Since you didn't crystallize the sugar cane juice into sugar, the sugar cane juice has a less sweetness and it's very delicious. So you might want to try it directly from the sugar cane sticks. So anyways, this is one of the advantages, okay, of your gas turbine, right? We can use different kinds and different types of fuels with these engines. So when you think of fluid, we know that that's liquid and gas. So here we're using the air, right? From where? From the outside, yeah, your atmosphere. We just draw it in. And of course, for this system, you don't need a coolant. You don't have to cool it down. Okay, all you do is just draw the air in or suck it in. Okay, fan it in, and then let the air meet with the fuel, and then heat it up. Yeah. Okay. So these turbines, or what it does, you already knew. We're turning, okay, fuel, okay, to power. So that's just an energy transition or energy transfer right there. Okay. So that conversion of different types of energy is very efficient, okay, for these turbines, because we can operate, right, these turbines at a very, very high temperature. Okay, it's a higher temperature meaning like higher efficiency, because you can reduce the cost. Okay, so meaning like here lead to more economical operation, meaning like you don't have to waste so much money into it. Okay, so using high temperature give you high efficiency. These turbines' capability is to turn the fuel into power, and it can go very low cost operation. Okay, so a typical power plant turbine. So it can go with 2300 degrees, so that's 2300 degrees Fahrenheit, of course. So that's where your gas is flowing. Okay, it's a very elevated temperature. And as you know, the turbines are made of metal, yeah? So that metal got to stand this type of temperature. But some of the turbines, they have limitation because the temperature, they can only take up to 1500 to 1700. So that's mean 1500 to 1700 degrees Fahrenheit, okay? So the metal of your turbine got to stand, okay? Be able to so I would say it in other words, it's got to be stronger than your temperature intake. Yeah? The atmospheric air, right, that we get from the compressor, since the temperature of that air is actually it's not okay as high as this temperature of the chamber. Okay, so it can definitely cool down turbine components. So what it does is it just reducing the overall thermal efficiency. Okay, it was just trying to tell you like since your turbines are made of metal, okay, and some of them can go only this much, yeah. Depends on the material of that metal, okay, what type of material, what type of metal that you're using to build that turbine. Sometimes they can go only that, okay. But even if we use a 2300 degrees Fahrenheit, they can still be able to operate, okay, at that level. That's because of this temperature balancing, right, or mixing, okay. So the air temperature and then the temperature of the system, they mix and reduce that temperature to where your turbine metal, okay, blades can be able to stand, okay. And of course the compartments, the metal compartments can be able to stand. So it's kind of like you can see the temperature transfer, then you can see the temperature equilibrium, okay, bringing very high temperature down to what it can be able to stand. And that is completely assisted, okay, and helped by the air, okay, coming in from your compressor. Because the air from the outside, right, that temperature of that air is lower than this, okay. So when you mix it, you will get the overall temperature, okay, which is your ultimate thermal efficiency, meaning like overall temperature reduces or goes down. Yeah? So since we have a material limitation, okay, and temperature, alright, you've got to solve those kinds of little issues. Yeah. So we boost our technology. So we have our Department of Energy, that's your DOE, okay. So they have advanced turbine program, okay. What are they doing? Okay, they break through the limitation, okay, previous limitations connected to your turbine temperature. So how are we going to solve the temperature issues? So they come up with a combination of new technology, okay, that is your cooling technology, and also using the advanced material, okay, material that can withstand the very elevated temperature. So they're working on cooling technology. If you don't have the right material and you need a very high temperature for some of the stuff that you're trying to do, then you got to come up with the cooling technology. If you don't have the cooling technology, but you do, okay, have some form of advanced material and you can, okay, make new innovative advanced material, then you can use that to build that turbines, okay. So play with the metal, play with the temperature, okay, mixing temperature with some form of cooling, okay, technology. So these are how we're solving the temperature issue relating to the system, right, elevated temperature, and the material, okay, of your turbine, okay, system. So by working on these issues, right, and then you research, of course, and then you develop better technologies. So the department's research, right, Department of Energy research, program so they can be able to boost the system temperature, which is your turbine inlet temperature, and we can go now all the way to 2600 degree Fahrenheit, so that's a 300 degree, right, Fahrenheit up from 23 normal 2300 system energy. So that's pretty good, yeah. So if you calculate the efficiency, that's about like 60% efficiency. So heat recovery system generator, right? It's just another way to boost the efficiency. Yeah. So we install something called recuperator. Okay, that's just like something that we use to recover the heat, waste heat coming out from the turbine exhaust. Okay, so you capture that and then use the heat. Okay, to preheat the compressor. So that's what we do. Yeah. So since you preheat the compressor, you don't have to mix the air, right? Your air and your fuel in order to get the heat to heat that compressor back. So we're using kind of like a recycling, capture the exhaust heat and then use the exhaust heat to heat the compressor. Yeah, and before you ever get the air in to the chamber. So so this approach, okay, to boost efficiency is nothing but so the first one is a recuperator and the other one is HRSG. So that's your heat recovery steam generator, and we call it HRSG. This is going to capture again, right, heat from your exhaust, the same thing as a recuperator, and then it's going to produce the steam. Yeah. So here is you reheat or the compressor. Here is you produce the steam by using that waste heat. And we call these boilers heat recovery steam generator, which is your HRSG. So in short, you can think of recuperator, use the waste heat, okay, and preheat the system. The other one, heat recovery steam generator, use the waste heat, okay, to produce steam. Okay, so not only steam, they can also, okay, produce electric power, electricity, okay. So that's pretty efficient. But of course, it's got to be very high pressure steam, yeah, from these boilers. So we call that kind of system or configuration. Because the HRSG generators, like, they are different, right? So for high pressure steam, you can also get electric power, and we call that a combined cycle. Yeah, I mean that kind of configuration or system configuration. All right, so this diagram is just showing you, okay, HRSG system. So that's your heat recovery steam generator. Okay. So you can be able to go back to your PowerPoint, right? Make it bigger, yeah, and then you can be able to read step by step, okay? So the same thing, using the waste heat from the exhaust, and we are producing steam. Some of the high pressure ones, you can be able to produce, okay, electricity. If you got the 2 key points, you're all right. These guys also have a turbine inside, okay? The same system anyway to generate electricity. Anyway, so get back to turbine efficiency. So if you have like a simple cycle gas turbine, okay, you can achieve energy conversion efficiency. So that's like 20 to 35%. Not very high because they're just a simple cycle. But if you got like a bigger system, higher temperature, okay, like those the Department of Energy, okay, use. So they are higher temperature combined cycle, right? Using hydrogen and also syngas fire gas turbine. So those kinds of system, okay, you can get energy efficiency about 60%. Okay, that's pretty high compared to our normal 20 to 35%. Okay, waste heat, and we capture the waste heat to use it. So in this system, the waste heat, we turn that around, right, for heating. Also, we turn the waste heat for industrial purposes. Okay, so the overall energy cycle efficiency is about 80%. It's kind of like a heat recycling right here, and that's your turbine efficiency. Smaller system 20 to 30. Okay, combined system you got 60, and for heating industry, if you calculate all of that overall, okay, both of these is going to give you about 80%. Yeah, relatively. Okay, so this is just for your knowledge, and I want you to just go ahead and read all of that. I'm not going to go over all of this thing for you. So anyway, so Lagoon Creek Combustion Turbine Plant, okay, is very is a big plant, okay, and that's in the west of Tennessee, okay. I'm not going to go over all of that. Just make sure you read it, okay, at least one time to get the information about this plant. You can also apply jobs, okay, right there. If you want to move to Tennessee, try that, okay. Maintenance major, you can go there. Um, and this is some more facts and figures for Lagoon Creek. So this plant, okay, they have like a 12 simple cycle combustion turbines. So that's a lot, yeah. And 2 combined cycle. It's a bigger system. It's just a regular system. So 12 of them and then 2 combined. This is just showing you like when they started to build. So 2001, and they completed in 2002. And then they got the combined system or units in 2010. The same thing, I want you to read from here all the way to here. Okay, I'm not going to go ahead and read all of that for you, but just for your knowledge. And this is in Mississippi, yeah, in Kemper County, Mississippi. You also got like a 12 turbines. Okay, so just make sure you read this slide at least one time. So they produce about 312, okay, megawatts. So that's your capability, and they've got like a 4, right, generator, so electric city generators, so 4 generating units, okay, producing this much of megawatts. So net capability, just a definition. So if you want to know what net capability is, you're gonna minus, okay, the power used by the plant itself, okay, from the measure of how much power a plant can generate for a specific time period. Okay, so every time we want to come up with standard, all right, amount, we usually measure. And here you are measuring. It's got to be always a specific time period. Okay, so that's how we standardize everything that we want to measure. So you can be able to compare, right? These standard numbers with whatever your current number is. So your net capability is, this is a formal definition, it's just a measure, okay, of how much power a plant can generate. Okay, your plant is generating this amount of power, and it's got to be within a specific time period. Okay, and then you're gonna minus the power used by the plant itself. You gotta get this out, all right, from this amount, because you don't want to include the power use, okay? Because power use is not your pure generating power. So if you want to know the the accurate generated power, okay, your electricity power, then you have to get rid of the power that you use for the plant itself. Yeah. Alright, construction, the same thing. They started 2001 and then they completed 2002. So you can be able to understand these are pretty new systems. Yeah. Okay, so this is just a picture. You can see these guys. Look at this, how big the turbine is, and that's your combustion turbine. Okay. You can get maintenance major. You guys can get a job there. All you have to just check here, check there, check everything. Okay. Maintenance major usually get a lot of money. Of course, they're gonna bully you when you start to work, and then you have to move up from there. But again, it's better to stick with the same company for maintenance major because your work, okay, gets easier and easier as you stay on. So these are the tricks, yeah. So here's another conversion or turbine that you can be able to take a look at it. You don't have to limit yourself to these pictures. You can Google it and go to many different sites and can be able to look at them because there are many different companies and corporations and industries, and they use different types of combustion turbines, and they come in different sizes. Okay. Again, here maintenance guys checking. Maintenance majors are pretty lucky because if you stay at one company, yeah, or one industry, all you have to do is the same job every day, because the system doesn't really change for a long time. Okay, so another picture for you to see. This is gas turbine combustor, and you can't be able to see it right now, so I don't want you to stretch, okay, into it. These usually, like when you start your job, then you will definitely get this system, okay, and system information, and you will definitely know the configurations, okay, and the parts, and also, okay, the entire big picture or blueprint, okay, of your system. So that's how you, anyway, understand the system that you have to take care of. Yeah. So this is just a picture for the gas turbine combustor arrangement. Here is another diagram showing you the plant basis, and that's your high temperature combined cycle. So you can see the steam out right here, okay, and we are using the heat coming out from the exhaust, and which is, you can see right here in this part, yeah. So this is your HRSG, and that's your exhaust track, and this is your cooling system because we're using the water. It means that your material is not so advanced, so we still use the water to um, make sure these temperature got to be in the range we want it to be, so not so elevated. Bring that temperature down because this entire part is connected to your combustion chamber. Here it's very aggressive, right? Temperature, ignition, everything's going on here, your gas expansion, and you gotta bring that temperature down when you generate your steam. Okay, you can also generate, of course, your electricity in addition to steam. Yeah. So you can see all three different parts of the system. So one is your recycled heat, use it, okay, bring down the temperature in the way that you want it to generate the steam, and then you generate the power. Yeah. So combined cycles, so they have like about 58 to 60% plant efficiency. Of course, they also have losses in mechanical input to the compressor and also the heat from the exhaust. Okay. For steam turbine, we're looking at about 50% of your gas turbine output, and that's very typical. And if you got like duct firing in your system, you get a little more percentage, okay, in your efficiency. About 24 months for construction time, and you have to put in about 80, to 130,000 labor hours, okay, and about 12 months, so that's a year for your engineering, okay. time. Money-wise, it's going to cost you like about 900, okay, to 1100. So that's $1,100, okay, per kilowatt hour, okay. So that's your capital cost. Of course, you can get that back when you got your electricity, and then you distribute that electricity to various residential and commercial and industrial places. Yeah. So the electric or energy bill, okay, you can be able to load this back out. Yeah. Profit, you always get profit from electricity generation. Okay. Because we use electricity every day, we have too many devices, and with what we're doing right now for going, okay, electric car, right, which is going to come after 2050, so we will be running all electric cars. Of course, you will definitely need power, yeah, which is your electricity, and we have to generate, okay, we have to generate to meet the demand, and that demand is going to come pretty soon, yeah, not so far away from now. Then we'll get into performance. So when you look at the factors, okay, the factors that influence the performance, we see these things. So the very first one is your fuel type, your composition, and then your heating value. Okay, don't worry too much about it, just read it, okay? If you got it, you're okay. Okay, quiz are not that hard. You can be able to do it. Load, that's your base, your peak, and your part, your compressor, okay, your inlet temperature, your atmospheric pressure, that's your air pressure, okay, your inlet pressure drop, which is very significantly, okay, depends on the type of your air, okay, cleaning or air cooling. So that's just the pressure, okay, pressure is nothing but your force of that air, okay, in a particular area in the system, meaning like how much air is pressing into the system. So that's what we want to know. And exhaust pressure, so another pressure so that we get around the exhaust, and usually affected by, okay, additional the HRSG unit or SRC or CO catalysis, okay. Don't worry about the SRC and CO catalysis. If you're okay with the HRSG, okay, recovery system, you're okay with that. And then your steam, this one just read through. Your steam, your water, okay, injection rate. So this is just to balance your temperature. Yeah. And they're used for the for power, okay, augmentation or your emission, okay, control. This is you don't, if you don't want to write it in nitrogen, all right, X, meaning like nitrogen monoxide, nitrogen dioxide, and then nitrogen trioxide, okay, you can just write it emission control, okay. And your relative humidity is another factor, yeah, that influence the performance. So you can play with all these factors if you want to improve your performance. Okay, I think you got it. Alright, so let's go to the next. Okay, so coal generation plant. It's going to produce steam, which is your thermal energy, and then that steam is going to be used by your customer, which is your thermal host. So your thermal hosts are your paper mills, your chemical plants, your refineries, and any user, okay, who's going to use steam on continuous basis. So those are your customers right there. Okay, cogeneration, so what are we cogenerating? You're cogenerating steam and electrical power, which is your electricity. Okay, this is just a video. You're gonna find this link in your PowerPoint, okay, from your previous instructor, or yeah, you're gonna find this link. I believe it's still right up on YouTube, so I'm not gonna run it the whole thing right here, just showing you your natural gas fuel combustion, all right, turbine, combined cycle electricity generator. system, and I want you to watch, right, that video. Okay, take time, go up there and then watch it. I'm not gonna run the whole thing right here. Yeah. All right, that's it for today.